Alrighty, time for another one. Question 4 from the 2018 AP Calculus AB free response question. This is a non-calculator question. Let's get to it. We see a chart before we even start reading. And so actually before we even start reading, we're thinking there's probably going to be a Riemann sum in our future. So let's do these intervals before we even know what's going on. There's an interval of 1. There's an interval of 2. Another interval of 2, and an interval of 3. So unfortunately, non-consistent intervals. So if we do some Riemann sum, we're looking at 4 separate calculations. Okay, so what are we actually looking at here? The height of a tree at time t is given by a twice differentiable function h. Stop there. Differentiable is a magical word in the AP world, and twice differentiable is like twice as magical. Differentiable always implies continuous, and twice differentiable implies continuous not just for the function but for its derivative. So this means h and h prime are continuous, which I'm guessing will come into play at some point in our journey through this problem. Okay, so the height of a tree t at time t is given by a twice differentiable function h, where h of t is measured in meters and t is measured in years. Selected values of this function h of t are given in the table above. Okay, we've already gone through and looked at those intervals. So we've got time in years and the height of some tree in meters. So let's jump in. Use the data in the table to estimate h prime of 6. Using correct units, interpret the meaning of h prime of 6 in the context of the problem. Okay, so we want to know an approximation of the derivative of this function at 6. Okay, so the best we can do is we can look around 6 and do an approximation there. So the h prime of 6 is the slope of the tangent at 6, so we can figure out the slope of the line between these known data points around 6. So, I guess I should pull out a piece of paper. One sec. Okay, so this is FRQ from 2018. Question 4. And we're looking at the height of a tree, and part A is asking us for an approximation of h prime at 6. Well, the approximation we're going to look at is the difference quotient of h of 7 minus h of 5, so around 6, over 7 minus 5. We can pull these function values from our table and get that h of 7 is 11, h of 5 is 6, 7 minus 5 is 2. So our approximation is 5/2. We need to throw some units on there. This will be in meters per year. So 2.5 meters per year. And so we get 1 point for that. But then we also are asked to explain what h prime of 6 means in the context of the problem. Okay? And so the way that the solution manual is written, you actually don't need to have the right answer to get the point for the interpretation. Okay, so even if you totally blanked and like couldn't really figure this out, you get the point here. But you could pick up a point whether you got this or not by saying the following: that h prime of 6 is just you showing the reader that you know what the derivative in this specific instance means. H prime 6 is the rate in meters per year at which the tree is growing at time t equals 6. I should put years. Okay, so without actually knowing what h prime of 6 is, you can get this point just by remembering what a derivative is and how it translates in a specific context. That's your second point. Cool. All right, part B. Explain why there must be at least one time, spidey sense, for this open interval, not quite, such that derivative of h is 2. Okay, this is like very, 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 very close to that magic formula that we've seen before, that at least one time, usually we want a closed interval, so that's a little bit concerning, but we'll see why in a second that that's okay. And then we see a derivative. Okay, so these three things, at least one time, usually looking for a closed interval, this an open interval, still an interval, and a derivative. Those three things add up to the mean value theorem. Okay. So the one hiccup here is that this is an open interval. We're usually expecting to see a closed interval. And what we're looking for is an interval where the endpoints, if we do the difference quotient, give us this slope that we're looking for, because then we know that somewhere in that interval the actual derivative has that slope. Okay, again, mean value theorem is like, okay, you've got these endpoints on a closed interval that have a secant line running through them. That slope has to be matched somewhere in that interval. And so we're looking for an interval within here whose secant line has a slope of 2. And so the closed or the open part here is a little concerning until we look at these endpoints of 10 and 2 and recognize, okay, if we actually took that difference quotient, so this is kind of side work, if we took, that should be an h of 10 minus h of 2 over 10 minus 2, that's not going to be 2. Okay, we get 15 minus 1.5 divided by 8, whatever this is, it's not equal to 2. Okay, so we need to find the closed interval in here where this difference quotient will give us a slope of 2. And so you kind of have to go hunting on this problem. It's a little bit tricky, but eventually you kind of can zero in and say, oh, okay, if we look at 3 and 5, 6 minus 2 will give us 3, 5 minus 3 gives us 2. Sorry, 6 minus 2 gives us 4, 5 minus 3 gives us 2, 4 divided by 2 is 2. That's the interval we're looking for, between 3 and 5 years. Okay? And so here's how we can do that. Here's how we can show this. Part B. We can do that difference quotient. H of 5 minus h of 3 over 5 minus 3. So this will give us the slope of the secant line between h of 5 and h of 3. And from our table we see that h of 5 is 6, h of 3 is 2, 5 minus 3 is 2, and so this turns out to be 2. Okay, and so we've got one of our conditions. We've got this 2 that we're looking for, because we're trying to show that there is a derivative somewhere in that interval that is also equal to 2. So before we can jump to say that that's true, we have to remember that the conditions of our mean value theorem require us to be differentiable and continuous, and so that's where this intro magic word comes into play. We can guarantee the differentiability and the continuity of h because of that intro. So we need to say that get the points, to say because h is differentiable, and here we're also going to introduce the closed interval. Okay, we can take any closed interval in this open interval. So because h is differentiable on the interval from 3 to 5, the closed interval, it is also not differentiable. It is differentiable. It is also continuous. And now we can invoke MVT. And by MVT, and again, readers will know what MVT means, there exists some, call it C, in the interval between 3 and 5, such that h prime of C is equal to 2. Box it up. For your points, you get a point for the correct difference quotient. You got a point for this, and you got a point for the conclusion inducing the mean value theorem. 2 points. Okay, part C. Oh, this is already taking a little longer than I thought it would. Part C is, oh, there we go, asking for our anticipated trapezoidal sum. So it says use a trapezoidal sum with the 4 subintervals indicated by the data in the table to approximate the average, that's an important word, the average height of the tree over the time interval between 2 and 10. Okay, so we do have a average value of a function theorem. The average value on a closed interval is the integral on that closed interval divided by the difference of the endpoints. Okay, so we're going to use this. We're going to use the trapezoidal sum to approximate this integral. And we're going to go to work. Okay, so the average height on our interval from 2 to 10 is going to be the integral from 2 to 10 of h of t dt divided by 10 minus 2. And we're going to use a trapezoidal sum to approximate that. So we'll get 1/8. 2 minus 10 is 8. Pull out the 1/8. And then the trapezoidal sum, we've already gone through and done the intervals. So each interval is actually going to be the height of our trapezoids, and then the bases are going to be these function values in our table. Okay, so our sum ends up looking like our base for each, which is, sorry, the height for each, which is the interval length. So 1 plus, or times, sorry, 1 times base 1 of 1.5 plus base 2 of 2 divided by 2 plus 2 times base 1 of 2 plus base 2 of 6 divided by 2 plus our third height is again 2. Our base 1 there is 6. Our base 2 is 11 divided by 2. And then our final height is 3. Base 1 there is 11. Base 2 is 15 divided by 2. And I would box that and go. But I know it makes a lot of us uncomfortable. But let's box first. It's all just math after this. I do see a 1/2 everywhere, so let's try to be savvy and pull that out. So this will turn into 1/16 times, let's bracket that, 3.5 plus 2 times 8 plus 2 times 17 plus 3 times 26. So 1/16 times 3.5 plus 16 plus 34 plus 60, 78. I'm already exhausted by this. I'm just going to check the solution manual. This turns into, yeesh, 263 over 32. So yeah, let's like not do that, please. But I guess it's your life to live and you can do what you want, but just box the non-simplified version. This turns into 263 over 32, which is just, no thank you. Points wise, you get a point for the setting up the trapezoidal thumb, and a point for the appropriate approximation. Okay, moving right along to last but certainly not least, part D. Part D is a little bit of a doozy, but I think if we keep our heads on straight, we'll be okay. So part D is actually a related rates problem. Oh joy. So let's see what they're asking. It is a long intro, so we got to keep our wits about us. The height of a tree in meters can also be modeled by the function g. So they're giving us a different function, given by g of x equals 100x divided by 1 plus x, okay, where x is the diameter of the base of the tree in meters. Okay, so x is the diameter. So it's not a function of t, it's a function of x. When the tree is 50 meters tall, the diameter of the base of the tree is increasing at a rate of 0.03 meters per year. Okay. According to this model, what is the rate of change? What is the rate of change of the height of the tree with respect to time in meters per year at the time when the tree is 50 meters tall? What? Okay, so what they're actually asking us for is the rate of change of the height of the tree with respect to time when the height of the tree is 50 meters tall. So they want to know g prime of x when g of x equals 50. Okay. Well, let's figure out when is that going to be. When is g of x equal to 50? G of x is equal to 50 when 50 is equal to 100x over 1 plus x. And actually, let's stop doing scratch here. Let's do it over here. So they're asking us, they want to know g prime of x when g of x equals 50. Well, g of x is going to equal 50 when 50 is equal to 100x over 1 plus x, because that is our function rule for g of x. To solve for x, we'll multiply that over, end up with 50 plus 50x equals 100x. Subtracting 50x from both sides, we get that 50 is equal to 50x. So this is going to be equal to 50 when x is equal to 1. So really we're looking for g prime of x when x equals 1. That's what they're asking us. Okay, well, let's figure out what g prime of x is. But before we do that, there was like this sort of sneaky piece of information they gave us that we didn't really talk about. When the tree is 50 meters tall, the diameter of the base of the tree is increasing at a rate of 0.03 meters per year. Okay, so this is a tricky little function because x is the diameter of the tree, and the diameter of the tree is itself a changing quantity. It is changing as time changes. Ew. But they give us a specific moment where dx dt, the rate of change of our diameter, is equal to 0.03 when x, when x is equal to 1, when that base of the tree, or when the height of the tree is 50. So this will come into play, this rate of change of our diameter. But let's jump into calculating the derivative of g. So g prime of x is equal to the derivative with respect to x of 100x, sorry, the derivative with respect to t of 100x over 1 plus x. And here's the crucial part. So when we take this derivative, it's going to have a chain rule because x itself is changing with t. The diameter of the base of the tree is changing as time changes. Okay, so we're going to do a quotient rule, but then we're also going to have to chain rule. So we'll take this derivative, but it's also going to turn into, it's also going to spit out a dx dt. Okay, so quotient rule. We'll have the derivative at the top, 100 times the bottom, 1 plus x, minus the top times the derivative of the bottom, which is just 1, all divided by the bottom squared. Okay, and you would feel so good about yourself having calculated this derivative, but then if you don't take the chain rule, the whole thing goes to heck. Okay? And so one way to think about this, and I'm not going to show it this way, but at each of these steps, when you took the derivative of 100x, yeah, it's 100, but then you also have to chain rule on the x to get dx dt, and so too here. When you took the derivative of 1 plus x, yeah, that turns into 1, but then there's also a chain rule on the x, which gives you a dx dt. So really there's a dx dt live in both of these places, and so we factor that out and get dx dt. Okay, so g prime of x is equal to this whole guy, and now this is related rates, and we're just going to plug in everything we know. We already figured out that we're looking for the derivative of g at 1, okay? And we also know the derivative of x with respect to t at 1, and so we're actually kind of home free here. We just got to plug and chug. So g prime of 1, yeah, that's fine. Let's just multiply this out. We're going to have 100 times 1 plus 1 minus 100 times 1 all over 1 plus 1 squared. I'm just plugging in a 1 for all those x's. dx dt, that was this guy, this 3.03. So let's write that in, but let's call it 300ths. 3 over 100. I think that'll work out a little nicer for us. Let's just go simplify this. This turns into 200 minus 100 over 2 squared times 3 over 100. Let's try heading this way. 200 minus 100 is 100 over 4 times 3 over 100. Oh, happy day. Hundreds cross out. And our derivative at that time is 3/4. And we need to put that into a nice conclusion. And again, this problem is like so convoluted, but let's go back and figure out what this represents. This is the rate of change of the height of the tree with respect to time when the tree is 50 meters tall. Okay? So let's, again, whenever we're in doubt about how to conclude something, we use the language they gave us. So according to the model, the rate of change with respect to time of the height of the tree when the tree is 50 meters tall is 3/4 of a meter per year. Box rep. Points was an all or nothing 2-pointer on the derivative of g of x, which if you didn't have the chain rule, you didn't get any of those points. So without the chain rule, you got nothing there. That was 2 points or nothing. And then you got 1 point for your answer. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 9 out of 9. And that was 2018 FRQ number